Yes. Right, so I will share my screen.
Right. So
the screen.
So thank you all, and welcome to the first seminar in our series this term. It's a very great pleasure to welcome Ard Lewis on an algorithmic version of Occam's razor in machine learning and biological evolution. So Ard is a theoretical physicist, but he's also a chemist and he's also a biologist. And he's also, I believe, been at a Centre for Natural Science. So perhaps it's that he's a person of all talents, and so particularly delightful to have you for that reason. And Ard is also a theist, and this is about Occam after all. So there's an Occam debate taking place in 2 or 3 weeks. Ard is for theism, I'm for atheism, and we'll see what happens to that. That also will go on YouTube eventually, but I'm not sure if everybody can be welcome to it because we have a small auditorium. So Ard, I look forward to that engagement, but this is not about that. So take it away. Lovely to have you.
Well, thank you very much for having me, Simon. It's nice to be here. I'm talking today about a wide range of topics, and I'll treat them hopefully not too technically, but I'm interested in some philosophical engagement on them. I think they're at least in convincing you that there might be some philosophical interests. So I'll start by giving a little overview of some ideas about simplicity, some of the historical backgrounds, different ways people have thought about it. Then I'll talk about a particular mathematical theory called algorithmic information theory that I think is helpful in this debate and could be and has been somewhat ignored by philosophers with a few exceptions. Then I'll apply these ideas to machine learning. And I'll argue that machine learning gives us a very restricted but very well controlled way of looking at questions about simplicity. So its great strength is that it's very well controlled. Its disadvantage is that it's maybe too simple for the kinds of things people might sometimes worry about. And then I'm going to, if I have time, talk about how these principles work in evolution, and I might end with some slightly crazy ideas. So I hope this works. I did a number of years ago. I did
it poses a deep mystery.
Okay, so let me just start this again.
We have
the sound is not working. Just try this again. Oh, it's not working. I'm going to try to maximize my volume on my laptop and see if you hear me. This is an interview with Frank Wilczek. So I did a film series. Actually, it was an atheist-theist kind of story. So my friend David Malone, who's an atheist, invited me to go around interviewing lots of interesting people. And so one of the people we chose is Frank Wilczek. So just to introduce you, Wilczek won the Nobel Prize in 2004 for asymptotic freedom, which is basically the theory of the strong force. He did this work when he was 21 years old. So he's a bit of a bona fide genius. Many other amazing things that he's come up with. So axions, one of the most popular models for dark matter, comes from his very fertile brain. Anyons, which are something between fermions and bosons, extremely important idea in condensed matter physics, came from his fertile brain. And more recently, he's worked on the asymptotic freedom, anyons, axions. There's a propensity for calling things by the letter A. And the last thing, which he's done more recently, called time crystals, which are basically systems which are in their ground state periodically moving back and forth without dissipating energy. It's been a huge source of interest by my colleagues in condensed matter physics. So we interviewed Wilczek on talked to him about what makes a great scientist, and he really wanted to speak about beauty. So I hope you can hear this because I want to pick up some.
A lot of beauty in our description of the world. It poses a deep mystery. Why should it be that way? Often when I start discussing this with people, they're very puzzled. Beauty is this subjective feeling that people have, whereas science is objective. How couldn't be more different?
I think that's a common view, isn't it? That beauty is merely subjective, it's in the eye of the beholder. And so what's really surprising is that this subjective feeling has traction on the physical world.
Yes, but there is a special kind of beauty, I think, that's associated with learning how the world works or making successful predictions for how the world works. And it makes very good sense from an evolutionary perspective that we should find those things rewarding. So that's a form of beauty that I think goes very deep.
You think it's an important one for science?
I think it's the important one for science. The idea of you get rewarded and you find it beautiful to make successful predictions about how the world works.
When you say beauty, what do you mean? Because obviously there are different kinds. What are the in physics and in science that you think this is
Right.
what is beautiful?
It's easier to experience than to describe. I think it has to do with structures that have a kind of inevitability, that you can't change them very much. An aspect of symmetry is that if you try to change a symmetrical object, like take a circle and rotate it, it doesn't change. And some of the most beautiful things in mathematics and physics have exactly that symmetry property.
The
Symmetry and productivity, or I call it exuberance sometimes, the idea that you get much more out than what you put in.
Right.
And a very small number of laws. You can write the laws of fundamental physics as we understand them easily on a t-shirt.
Right.
And
the universe pops out of
the universe pops out. That's
Okay.
Yeah, so I thought I would listen to that because he's one of our greatest living physicists, clearly very successful, and he's telling us that the way he finds new ideas, incredibly fruitful new ideas, is he starts by talking about beauty, but I wanted to actually move away from beauty a little bit. I think what he's really trying to say is, well, it's really about those few laws. In the end, he says you can write them on t-shirts. And somehow that's where the fecundity, the productivity, or the exuberance comes from. And interestingly, he has an evolutionary argument for why this works. That somehow we get rewarded for this. It's obviously not, may or may not be true. It's very susceptible to kind of evolutionary debunking arguments. Why would the way our brains work on the savannah have anything to do with axioms? This is, of course, a well-known furrow for philosophers to plow. I want to point out because in the end of the day, I think what he's really talking about is some kind of feeling, a gestalt, something that you catch, something you understand. And very famously, the judge who was asked, could we give a definition of the difference between pornography and art? He said he couldn't, but I know it when I see it. And there's a kind of sense of that nature there. And I think in the end of the day, what you're seeing with Wilczek and many other physicists, many other scientists, is a kind of grasping for something like simplicity. He's talking about something that helps him make successful theories. It's clearly very productive in his mind, or this is how he tells himself. What he tells himself is what he's done. And I think that feeling, that sense, is something I've always been very interested in. What is it about physics or science in general that makes us do this? There's many different ways of thinking about it. And Occam's razor is actually one particular way, probably the most popular way of thinking about that. And so rather than using his language of beauty, I think he's really talking about some kind of simplicity, something like Occam's razor. So I'm going to unpack that idea a little bit at the beginning of my talk, which is going to be the vague part of the talk. And so Occam was possibly at Merton. So you can tell me if he was at Merton. I think it's certainly, yes. And it's probably the most famous formulation of his because the entities are not to be multiplied without necessity. And this comes from John Punch's commentary on Duns Scotus. What he actually said was plurality is not to be posited without necessity, or somewhere else he said it's futile to do with more what can be done with fewer. And you can see the whole, if you look at the statement in Meredith, you can say, as has often been said. And this is because Occam's idea of Occam's razor is really an example of Stigler's law. Stigler famously, a statistician at the University of Chicago in 1980, gave the law that basically every law is not named after the person who came up with it. And he claims that Robert Merton came up with this idea, which is why it's an example of Stigler's law. And so you see many, the point is that whether Occam was really talking about anything like the razor that Wilczek was kind of indirectly referring to isn't clear. I mean, Occam was obviously a nominalist, was against universals. Some people argue that really this Occam's razor had something to do with his arguments against universals. In fact, I know there's one or two theologians in the audience. There's an interesting kind of, one of the most fruitful theological or most interesting theological developments of the last few decades has been radical orthodoxy. This is one that's has caused the most noise. And they basically claim that these kinds of statements by people like Occam and Duns Scotus were the source of where theology all went wrong. So it's interesting in that sense. But you can see that Robert Grosseteste, another Oxford man, possibly the first chancellor of the university, another great polymath wrote, in natural science, in moral science, and metaphysics, the best is that which needs no premises, and the better that which needs the fewer of the circumstances being equal. So this is a kind of a statement that says, all things being equal, best to take smaller number of premises. That's a kind of something like entity should not be multiplied without necessity. And Aquinas, who was around another scholastic, said, if a thing can be done adequately by means of one, it is superfluous to do it by means of several, for we observe that nature does not employ two instruments where one suffices. And Duns Scotus, who was his teacher, also an Oxford man, so only Aquinas didn't quite make it here as far. Did Aquinas make it to Oxford? Not sure he did, but the other three, other place, yeah, maybe. Did he? That probably explains a few things. But Duns Scotus said we should always posit fewer things when the appearances can be saved thereby. Therefore, in positing more things, we should always indicate the manifest necessity on account of which so many things are posited. And in fact, if you look more carefully, they were just repeating things that the ancients had said. So Aristotle has some quotes here. I won't give the great detail, but he also says nature does nothing in vain, which we'll see come back in a minute. And Ptolemy, of course, famous for a not very simple system of the planets, nevertheless said, we consider a good principle to explain the phenomena by the simplest hypothesis possible. And if you keep going on, we see many other greats. So Newton, in the second version of Principia, wrote this. He had 3 rules of doing science, basically, what we now call science. And the first one was, no more causes of natural things should be admitted than are both true and sufficient to explain their phenomena. As the philosophers say, nature does nothing in vain. That's quoting Aristotle. And more causes are in vain when fewer suffice. If you actually, my Latin is not very good, but people that know Latin tell me if you look at the Latin that Newton uses here in the Latin from Duns Scotus or Occam, he's clearly quoting from them. So he's taking this from these era people. And so if you actually look at people like Newton and a lot of his contemporaries, this idea that simplicity was a good thing in science was often driven by the idea that because God would create a world that's simple. So the justification was God would like to create things that are simple, perhaps because they're beautiful, and therefore we should expect something like this to be true. Another one of the real greats in science, in physics, Maxwell, who knew about the unification of electricity and magnetism, talks about this as well in some detail. And he actually turns the argument around. He says, well, simplicity works really well. And therefore, this is some kind of evidence for God, because if there was no God, then you might not expect the world to be simple or explainable. And those are the kinds of the way the history went. Now, just saying that God did it is not necessarily that useful. And in fact, if you look a bit more carefully, Leibniz had the best of all possible worlds, a kind of principle of plenitude. See, from God, you can also come up with ideas that seem to be an anti-Occam-like argument. So it doesn't necessarily solve this problem very easily. And the big change really in the 20th century and onwards has been a kind of probabilistic turn. So very famously, Jeffreys, one of the fathers of modern probability theory, gave a very simple kind of, so he was this is where things turned to using Bayesian arguments. There's also the very famous question of the first prior. And Jeffreys basically said you should pick, you should give your first prior higher priority if it's simpler. And so you'll order all your hypotheses by the number of parameters. And how do you define simplicity? You've got to define it by the number of parameters that you put into the theory. And so simpler theory should have higher initial priors than later one, than more complex ones. And this is how you start out your Bayesian inference, and then you turn your crank. And he famously talked about Lin and Parr. So Lin is a linear theory with just 2 parameters. Parr is a quadratic one, and you can think of higher and higher order ones. So Lin is simpler than Parr, and so Lin is referred over Parr when you first start. There's a very famous debate between Jeffreys and Popper about this. Popper thought this was wrong because clearly Lin is inside of Parr if you just send A2 to 0, right? And so therefore he said this whole thing can't really work, and therefore Popper said you can't really use this kind of arguments. But if you, as he tried to do, solve the demarcation problem with falsification, then he said, therefore, Occam's razor is still saved because simpler theories are easier to falsify than complex theories. If I have 2 parameters and I only need 3 points to see that I can falsify it. If I've got 3 parameters, I need 4. I need more. The more parameters I have, the more data points I need to falsify the theory. So therefore, on this basis, simpler theories are better. And so what you see here, and I've kind of skated over a lot of things, is there's a kind of continuum between people that make kind of ontological arguments about what Occam's razor is, to kind of epistemological arguments that say this is a better way of understanding things. They're referred because they're easier to falsify, for example, etc. There's another kind of Oxford laid razor, which I'll call Einstein's razor, which has been quoted on t-shirts: make things as simple as possible, but no simpler. And the Oxford connection is because, as far as we know, he never said anything like this. That was a gloss on other people. And the closest thing I found is from a lecture he gave in Oxford, the Herbert Spencer lecture, the man who coined survival of the fittest. Stigler's law, perhaps he didn't, perhaps somebody else did, but he did. So what Einstein really said is, it can scarcely be denied that the supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible, without having to surrender .
I'm sorry, but the speaker is muted.
Okay, I think it's fine now. How about, is this better? I think I was muted. I think, unfortunately, I was muted. I apologize. I think I was muted. It may have. How strange. All right, so I will. Is that better?
I think so.
Good. I'll turn off my volume, but I will mute myself. So there's another great, two great physicists, Freeman Dyson and Enrico Fermi, and in a very charming little story that was written up in Nature, Dyson talks about traveling across the country from Cornell in New York all the way to Chicago to meet with Fermi, because he had a new theory of the weak force that he wanted to show Fermi that he thought fit all the data. And famously, Fermi asked him, well, how many parameters does your theory have? And he said it had 5. And then he said, well, my friend Johnny von Neumann's told me with 4 parameters I can fit an elephant, with 5 I can make it wiggle its trunk. Actually, there's a paper in the American Journal of Physics that shows that you can indeed do this. You can use 5 parameters and draw an elephant and make it wiggle its trunk. And the argument is basically, if you have too many parameters, so your theory is too complex, and you can fit any data, okay? And this is a bad thing, because it probably won't be this could be, you could be fitting it for some kind of false reason. We're going to come back to that intuition in just a minute. And this is often all seen as a kind of Occam's razor type argument. You know, you should try to minimize the number of parameters in your theory, minimize the number of hypotheses, and the less you have, and you can still fit all the data, or fit the data well enough, the better and more likely your theories to be true. There's lots of recent approaches on this. There's a very nice book by Elliot Sober, has a particular take on this. There's lots of interesting approaches by Bayesians. David Mackay, very famously on Bayes factor. I think it's not quite right. Kevin Kelly at CMU talks about justifying Occam's razor as he tries to prove that you can, if you use Occam's razor in some kind of inference, then you're the least likely to get the wrong theory after new evidence comes in. It's an influential new idea. Alan Baker from Swarthmore has a very nice paper that then got turned into the Stanford philosophy encyclopedia page on simplicity, which I think is quite nice. And he points out there are really 2 kinds of razors. One is a kind of elegance, or 2 kinds of versions of simplicity. One is elegance, so syntactic simplicity, the number and complexity of hypotheses, and the other one is parsimony, so ontological simplicity, so the number and complexity of things that are postulated. An example he gives is, well, if you may know this, that when the planet Neptune was discovered by looking at the orbit of Uranus and noticing that there were slight deviations in that planet that couldn't quite be described by gravity. So you could have two options. One is to change your theory of gravity and have that explain Uranus, or there could be some hypothetical planets out there, which if you do that, then allows you to retain your normal Newtonian gravitational physics. And he says this is an example of elegance winning over parsimony, because you've added a component to your theory, you've added this next other thing, but then you get the simpler theory. And I think that is really what people like Wilczek and many physicists call beauty or something. It's some kind of elegance. It's the idea that there's something about the theory that reduces the number of hypotheses, perhaps, or the complexity of hypotheses, and you can, by doing that, describe more data accurately. And if you can do that, if it predicts something, particularly if you can make predict something you didn't know, and then it turns out to be true, and that's a very good guide for the accuracy of your theories. Interestingly, for example, Sober really only talks about parsimony. He just says, Occam's razor is about ontological simplicity. It's the number of objects that I have in my theory, the number of concepts, the number of units. And this gets into the problem of thingness, right? So what is a thing, right? How many things are there? And it's not so clear to me that these can be distinguished that easily. And the kind of questions that you can have about Occam's razor, or maybe simplicity more generally. So you could say Occam's razor is really something about simplicity. Many people have, over time, think that simplicity has some kind of has some benefits to it. And the question is, how is it defined? It's kind of definitional questions. What is the role that it plays in different areas of inquiry? So I'm going to be mainly interested in science, but Sober looks at some detail of whether this is or isn't a good guiding principle in philosophy, for example, where it may or may not be, or in theology, where it may or may not be. And then is there a rational justification for this symmetry principle? So some kind of justification. So I'm going to be interested really in all three of these questions. I'm going to give you some kind of definition of this and some kind of ways of using it, and then give some kind of justification for it in a restricted area of inquiry. Okay, and so before to do that, to kind of give you a definition of simplicity, I think is going to be very useful. I want to segue for a second into a different question, which is a question about algorithmic information theory. And algorithmic information theory is a really beautiful mathematical field. It has to do with the complexity of individual strings. And the reason I was interested in it is because the reason it might be interesting in the way I'm going to approach it, to explain it to you, is actually the historical way it first came about. It's not the way you normally taught it in school, not in school, in university. Actually, you're not even taught it. It's almost not taught. But if you read the books, it's not the way you're taught it, but perhaps it should be. And that's by giving you a very simple analogy. So it's basically this intuition. So there's a very famous trope of monkeys on keyboards. Now, traditionally it was on typewriters, since many younger people in the audience may not know what typewriters are. Let's assume just a word processor. And the question is, how likely is this monkey, by randomly typing, to get the digits of pi? Well, if there are n keys on the typewriter, then to get it right at each time, it's got to get 1 over n chance. 1 over n chance of getting 3, 1 over n chance of getting 0.1, 1 over n chance of getting 1. And each time it's equal and random. So actually, probably the monkey will get this m digits right is 1 over n to the m plus 1, because you've got to get the 0.1, 3.1. That's the number you need to get right. That actually becomes incredibly small very, very quickly, but it's possible. But of course, the probability that the monkey will get any string, including a string of all zeros, or just a string of gibberish, or a string that says something like to be or not to be, they're all equal to each other. And that's the kind of the point of this kind of argument. But of course, what if instead of typing into a typewriter, the monkey was typing into a computer program? Let's say that there's a computer program that's like C, for example, and the monkey is accidentally typing into this. Well, then actually the probability of pi is going to be much higher. Pi is an algorithmic number. There are algorithms that will generate it. And there's a competition, in fact, that for generating the shortest program that makes pi. And here is this program by Dick Winter from in Amsterdam, and it generates the first 15,000 digits of pi correctly. And so the monkey, it's only 133 characters long. So the monkey has a finite probability 1 over n to the power of 133, still extremely small, but much, much larger than 1 over n to the 15,000 of typing this out. So the intuition is, if I look at the outputs of an infinite number of monkeys with an infinite amount of time on a computer screen, I just see what comes out. I don't necessarily see what the process of it. I can distinguish between a an algorithmic input, so then it gets some input that gets turned into programs, and simply the input equals the output. And I can distinguish them because certain objects that have short descriptions will appear exponentially more likely in the second scenario than in the first scenario. Does that make sense? So that's the intuitive arguments that I'm going to try to expand on a little bit. If you normally talk about algorithmic information theory, it comes in the language of what's called Kolmogorov complexity or Kolmogorov-Chaitin complexity. There are also these are a bunch of great geniuses, two great geniuses, Kolmogorov, whose name is everywhere in science, Chaitin, who had this idea when he was first 15, and then published it, I think it was 18. And so the argument that they basically say is if you have a string, let's take for simplicity a binary string, you can map any sequence onto binary sequences so you don't lose any generality. Then the intuition is something like this. This string, which is 50 0 ones in a row, is simple. This string, which is basically just a string with, as far as I can know, no shorter description than just print the string, is complex. And so formally, what they showed is that the best definition of the complexity of the string is the length of the program that will generate that string on a universal Turing machine. So universal Turing machine is a generic model of computing. A universal one is one that can do any computation. And one of the beautiful things about this definition is because the universal Turing machine can simulate any other universal Turing machine, it's effectively machine independent up to terms that map you from one machine to the other machine. So it's a fundamental thing that isn't machine dependent. And asymptotically, of course, if you've got small programs and the compiler terms might be big, but with big programs big strings, bigger programs, that should be negligible. And so effectively, asymptotically, your complexity is just something called the Kolmogorov complexity. Now, the difficulty with it, of course, is because it's done on a universal Turing machine. Famously, Turing came up with universal Turing machines in order to prove that there are things that are uncomputable. He very famously did this and the way that he showed this is taking Gödel's undecidability theorem and turning it into an algorithmic computational language. And the way this works is that you can prove that you can show that it's unprovable to be able to predict that your universal machine will halt. So you don't always know. So you can run through many programs and never output this string because there might be one if you waited long enough, it would, right? But it might run as long as the age of the universe before it does. And intuitively, what this is telling you is if I give you, in fact, the digits of pi, they're actually Borel random. That means they're any statistical test you can do on them, it's completely random. So it looks random to every test that we know about, and yet it's not because I can generate it with some kind of short program. And so the idea is that's an intuitive way of understanding something about the uncomputability. So if I just give you a string, I don't know whether it might have some short description though. And so this is a really interesting and powerful set of ideas because it gives us kind of interesting intuitions. One of the intuitions is what's called, which is a formal way of defining a random number. What's a random number? It's a number that has no code other than just print number. It's called Morton-Luff randomness. That's kind of intuitive definition, but that's the formal definition if you want to have a random number whose Kolmogorov complexity is equal or larger to itself. Equal or larger to itself because you've got to print it, so you have to have a little print statement at the beginning, so it's slightly larger than the sequence itself. The other kind of intuitions you get is like ones like this one. So the complexity of a set can be much less than the individual elements of the set. So if I say to you, write all numbers from 1 to googolplex, that's a very short description. But there are very complicated numbers in that set. And so you can think about it this way. Those are interesting intuitions. Now, this is where Stigler's theorem comes in, because the man who first actually had these ideas was Ray Solomanoff. So Solomanoff was a student of Carnap, a famous philosopher, was interested in induction, and he decided to look at this problem of universal Turing machines. And so prior to Kolmogorov and Chaitin, he asked the question, what happens if you randomly type programs into a universal Turing machine, which is exactly the monkey typing on a typewriter? And I'm going to simplify now, as Solomanoff did, to binary programs. So all programs can be written in binary codes. So you've got a monkey now typing on just two keys, 1 and 0, or typing randomly, how likely is a monkey going to output a particular sequence X, like the first X digit, some certain number of digits of pi, for example? Well, it's a sum over all programs that will generate X times the probability that that program is generated. Well, that probability that that program is generated is 1/2 to the power of the length of the program. So sum over all programs times the probability of each individual program. Does that make sense? And then Solomov's intuition and Solomov's great idea was that the shortest program is going to have the largest probability to appear. It's obvious, right? If you randomly type, the shortest program is going to be the largest, the most likely one to appear. So the first term in this sum is 2 to the minus k. And so the concept of Kolmogorov complexity had already been worked out by Solomonov prior to Kolmogorov. Kolmogorov came up with it independently. Later, in fact, very famously, when he discovered this, Solomonov never had a famous affiliation, was kind of an eccentric person, a bit on the fringes of academia, but a great genius, clearly. And Kolmogorov invited him to Russia, and admitted that it was he wasn't the first person to think about it. But the Kolmogorov complexity is what we now call it. Was right, I write K right there. And interestingly, I mean, Marvin Minsky, who's one of the fathers of AI, wrote this. I said this in a talk not too long before he died. It seems to me that the most important discovery since Gödel was discovered by Chaitin, Solomonov, and Kolmogorov of the concept of algorithmic probability. So this is algorithmic probability, the probability that you generate an output upon randomly typing random programs into a universal Turing machine. Now, this argument by Solomonov only really gives you a lower bound, right? There's at least one program that generates an output. If it's the only one, then that is the probability. But if there are more, the probability is going to be higher because you might type longer programs. And the really kind of deep thing with Leonard Levin, again, there's a series of geniuses, also famous for P versus sorting out P versus NP, with deep problems in computer science. So basically show that not only was this a lower bound, so there's at least one program that generates that output, but it's also up to order 1 terms, up to constant terms, it's an upper bound. And that means that there are terms that are independent of the outputs that you're trying to generate. And this is the algorithmic probability really that Minsky was talking about. And it's a very interesting object. It has all kinds of very beautiful properties. You can prove that it's in some sense, a better probability distribution than any other probability distribution. So it's a very deep mathematical object, even though it's fundamentally uncomputable because Kolmogorov complexity is uncomputable. It is a very deep, just like K is uncomputable, P is uncomputable. It's a lower semi-definite probability distribution because some of the programs obviously won't hold. And the history of this is that I was working on some problems in evolutionary theory where I saw a strong bias towards simple outputs. And I sent a mathematics student of mine on a wild goose chase trying to find some theory that would give us some handle on why we were seeing what we were seeing. And he across Levin's coding theorem, which I think is an absolutely amazing theorem. I really think it ought to be taught much more widely. It basically tells us that universal Turing machines, if you randomly type into them, are going to be exponentially biased towards simple outputs. The problem is, of course, and one of the reasons why it hasn't been really perhaps not taught in engineering departments or in physics departments is because, of course, many systems aren't universal Turing machines. K is uncomputable. And also these results only hold in, you can only prove them to be true in certain asymptotic limits. So the interest has largely been in kind of formal theories about induction, formal theories about statistical inference, and people are interested in properties of universal Turing machines and kind of foundations of mathematics. And that's, I think, why it's kind of been a little bit unloved. But it's an absolutely amazing theorem. It's about 50 years old now, almost 50 years old. It's really very, very powerful. So what I decided to do with some very bright students is to try to come up with a simpler derivation of this that doesn't use all technicalities, doesn't work with just universal Turing machines. And we ended up, after a lot of work, coming up with a very simple kind of idea. And I'll give you a proof sketch. It works a bit like this. If I have a simple map, so maps from inputs to outputs, Okay, so any kind of computer can be an input-output map, right? I put inputs and it gets output, so it's input-output is a very generic thing. So I've got some input-output map, and now I'm going to have inputs of size n. So that means I've got some alphabet of size 2 to the n, for example, number of inputs. What I can do is I can calculate all possible input-output pairs. That takes very little information. That's just a set of all possible input-output pairs. I just tell you calculate everything, and that's it. So it doesn't take very much information. Then I can also calculate how frequently certain outputs appear. So if certain outputs appear with more more frequency, higher frequency than others, it's also a very, in terms of information theory, a very cheap thing to keep track of. And then there's a well-known set of ideas from kind of Shannon information, coding theories, that tell you the most efficient code that you can write down is a code where the probability of an output goes as half to the power of its length, or the log probability is proportional to its length. So the idea would be, if you have a whole bunch of different outputs with different frequencies, you give short code words to the frequent things and long code words to the long things, and that way you can make the most compressible code. And so if you use that idea, that's one way of generating any particular output. Right? So what's the complexity of a particular output? I run this little sequence of things. None of the steps actually take that much information, right? Then I basically say, well, the complexity is going to be lower bounded by the length of the code word that I gave to that object. So this is one way of generating some estimate of the Kolmogorov complexity. The true complexity could be shorter because there may be a short description of this. This is at least one way of calculating this. Plus, there's these order 1 terms, which are the terms that the costs that it takes me to do that procedure. I can just turn that into, that's basically this log, these lengths are exactly these logs, and I can rearrange the terms, and I get the probability of getting a certain output is less than or equal to 2 to the minus complexity of the output. I've got a problem because conditional on a particular input-output map that I have to know has to be given to me, right? And the size of my input space, which I have to know, has to be given to me. So it's not quite as nice as the Kolmogorov complexity I had before, which is just a universal property of the output. Now I've got something which I need to tell you something about the input and the output. But of course, what's nice is if my input-output map itself is simple, so it doesn't take a lot of information to describe, then it is also a relatively small term. I can bound my true complexity from my conditional complexities, and I'll get this lower bound. So the probability of getting a certain output is less than or equal to 2 to the minus the complexity of the output given x, given f, given n, which is the first order independent of f and n. And then to make it practical, I can't calculate Kolmogorov complexity. So I've got here this k squiggle. This always worries our referees to no end. It's basically some approximation to Kolmogorov complexity. So Kolmogorov complexity is something like the shortest description that generates something. It's very closely linked to compression theory. So if I have a file on my computer, I hit zip the file, then what I'm doing is some algorithm is compressing that file. It's trying to find the shortest description of that file that will generate the output. And so there's a very sophisticated and actually huge amounts of money has been poured into research to make these things as efficient as possible. And so typically we say, well, use some kind of compression algorithm on your outputs. That'll give you some, that's a bound on Kolmogorov complexity that may not be too bad. And so what we have is basically some effective approximate of Kolmogorov complexity. It may not be perfect. And if it'll only work if I don't have too many algorithmic outputs. So things like pi, which is uncompressible, but actually has a short description that I may not know. And so I'm making some assumptions about the frequency with which these kinds of objects appear in the world. And so here I just want to show you very briefly how this works. And I'm going to pick just one example from a whole series of examples. We can also break it if we know how to break it. So if I make the input-output map complex, so the inputs are mapped as a very complicated map, then this argument doesn't really work. But if they're not, then this does work. So here is an example of something. These are called L systems. So they're little, it's a little algorithmic shape that says basically make a line and then make a branch with some probability. It's originally by Astrid Lindemeyer, a botanist in Utrecht. It's now used widely in computer graphics. So if you ever watched movies like Avatar, they generated those images using L systems. And so what we show is if you just randomly, if you make L systems, you just instead of trying to make something pretty, you just randomly type programs in, then you're exponentially more likely to get simple programs linear complex programs, and we can predict roughly what that probability looks like. And although we only predicted upper bounds, we can show, it's a different story, that the majority of the probability weight is close to the bounds. And so that's nice. This thing works pretty well. So here's this kind of coding theorem that Levin worked out, and we have our simpler coding theorem. And if there is actually a very interesting literature about whether this can be used to justify Occam's razor. So people like Marcus Hütter, Paul Vitagni. So Hütter is a very famous person in the field of AI, very interesting thinker, is now part-time at DeepMind. Vitagni is kind of wrote the big textbook on AIT, and they both have articles where they basically claim that they can justify Occam's razor based on this coding theorem. The argument is that this gives you a universal prior, it solves the problems of your initial priors. This universal prior, this is a prior to a simplicity, and that you can prove that this is always the best prior, and therefore they've solved this very famous problem. And they've written about this at some length. It hasn't really been touched much by philosophers until Tom Sterkenberg, a Dutch philosopher, took it on about 5-10 years ago. And he's been looking very carefully at this and claims for very subtle technical reasons that doesn't quite work. It's definitely a super interesting topic. And so I think if there's anybody in the audience who's interested in inference, this is a very fruitful, I think still still unexplored direction of kind of theoretical mathematics, of inference, of philosophy. And I think there's some need to still need to kind of tie these things down and understand them. And it's super interesting. So they basically say, look, everything can be, universal machines can calculate anything by Turing theorem. Therefore, this tells you that simple things are exponentially more likely to appear than complex things. Ergo, this is a good prior. It's roughly what they're saying, but in more sophisticated language. And therefore, they're claiming it solves all kinds of problems. I don't think it does. So I think that they're not quite right, but it's nevertheless interesting, and I think it needs to be sorted out in more detail. All right, so that's an introduction a little bit. I give you a kind of a hand-waving introduction to some concept of Occam's razor. The main point of that was to say Occam's razor is a slightly vague concept. I used Frank Wilczek's little video to kind of show you that this is a slightly vague concept, even though if something like it seems to be working very well, we don't quite know how to put our fingers on it. So look, you're trying to understand it more carefully. It gets very slippery. Is it ontological? Is it epistemological? Is it elegant? Is it parsimony? All these things, not very clear. I think maybe there's perhaps many Occam's razors if you want to use that language. So what I'm going to do now is look at a very specific subset of these ideas using machine learning theory. And I'm going to argue in this, we have a really good handle on what the complexity and simplicity is, and we can also define these terms relatively well. And that might give us some ideas as well about how you could think of Occam's razor. And I think, again, for philosophers, there's a lot of interesting work in machine learning that would benefit from some close philosophical scrutiny. So the idea of learning machines comes from Turing again, one of his many great ideas. Apparently, he did this, I forget the name is where he was working at the time, but he asked for time off to work on these ideas. His boss told him that his paper that he wrote was like a schoolboy's essay and didn't want to publish it, but it was like full of really deep and interesting ideas. And what Turing basically says there is, instead of trying to produce a program to simulate the adult mind, why not rather try to produce one that simulates the child's? If this were then subjected to the appropriate course of education, we would retain the adult brain. We thus divided our problem into two parts, the child program and the education process. And one way of thinking about this is something people call supervised learning. So machine learning is a broad word for a wide range of methods that you use a computer to basically learn from data and infer from data some kind of rules that you think will work on this unseen data. So a classic kind of problem works like this. You have some training data. So these are handwritten images of letters from 0 to 9. So the endless data set's very commonly used. And the idea is you train your learning algorithm to recognize that this is a 0 and that's a 1, that's a 2. And if you do that well, then if you give it new images that it hasn't seen before, it'll correctly tell you what the letters are. That's an example of, you're learning something about the data, so you're training it with this data. That's the child's process, the training process. Then you test it on this. And the thing you care about is this idea called generalization. And that word generalization is there because you've learned that on here, can you generalize to new data that you haven't seen yet? Can you explain things that you haven't yet seen? That would be the idea. So you do some kind of adaptive learning. And it's a very, very famous kind of way of thinking about these things. And there's a very big and sophisticated field. And here in our university in computer science, statistics, and mathematics, where you find people working on this. Many very smart people have made careers on this, where they try to say, if I do this kind of process, try to learn how complicated should I make my machine that learns these algorithms. And the thing, what they talk about is the risk. You see on the y-axis the risk. The risk is basically how likely are you to make an error on unseen data. So how likely to not generalize well. That's your risk. And then you want to minimize that risk. So minimizing the risk means that in this case of zeros and ones and 1, 2, 3, so sorry, 0 to 9, if I give you an image of somebody handwriting number, you get it right. This is a practical problem. So if you have an automatic check reader, for example, you want to get the numbers right of how much money people are writing on there. You don't want to get it wrong. So you need to get this, you want your risk to be small. And what statistical learning theory, which is a very sophisticated branch of mathematics, has shown is that as you increase the capacity of your problems, the complexity of your set of hypotheses that you're training on your data, initially your error goes down. And that's because there is some kind of ground truth process which generates the data. So in the case of handwriting to numbers, some kind of ground truth image to label function. If your system is too simple and it can't capture it, you're going to have bias problems. Okay, so you're going to have a bias, which is basically that you can't properly describe that data. So the more complicated you make your system, the better you're going to predict the future is the idea. Same thing as if I have the same exact principle. If I have a bunch of data points and I fit it's too simple a polynomial through it, I won't be able to fit the data. But at some point, then what happens, you start getting what they call variance, which basically says as your model becomes more complex, you run into the following problem, which is that you may have many different hypotheses that can fit your data, and you don't know which one to pick. Okay, and so you start getting because you only have a limited amount of data, and so therefore you start getting errors where you overfit. So you fit your data, but you're actually fitting stuff that's not really there. And so somewhere in between those two is the balance. And I was just listening to a lecture on this topic earlier today, very famous online lecture, and the lecturer said, this is the most important lecture of the whole course on statistical learning theory. Bias variance trade-off separates the adults from the children in machine learning. If you understand this, and this is the fundamental way of understanding machine learning. And so why this is interesting is because this capacity, there are very subtle measures of capacity like VC dimension, radar complexity, a whole series of ways of calculating this. These are very, very careful ways of defining the simplicity that you care about. This is a kind of Occam's razor like argument. Or so basically, it's actually, I think it's an Einstein razor really. You want to make it as simple as possible, but no simpler. Make it too simple, you get errors this way. If you make it too complex, you go that way. And somewhere between this is Occam or Einstein razor captures. And statistical learning theory has worked this out in great detail and has worked out very subtly what the best way of measuring the complexity and simplicity is. And actually, very roughly speaking, it turns out their simplicity measure is a kind of parsimony argument. Basically, you count the number of hypotheses that your machine can measure, and you want to limit the number of those hypotheses. So if the number of hypotheses is small, then that would be that would tell you your model is simple. You want to kind of control that capacity. So that's the kind of idea of machine learning. I want to step very briefly, take a little aside just for your amusement, perhaps, to talk about where this has taken us now, why is it so popular now. So machine learning is a subset of kind of artificial intelligence ideas. And there were this Turing's paper came very early. There were automated translators, and there was something called a perceptron. And in 1957, Rosenblatt, which is a very simple machine learning technique. And in the New York Times in 1957, they wrote, the Navy revealed the embryo of an electronic computer that expects to be able to walk, talk, see, write, reproduce itself, and be conscious of existence in a very short amount of time. So there's a huge, so this field of artificial intelligence has had these hype, as you can see, this is clearly hype that happened. And then AI winters. And so very famously, Minsky, who I quoted earlier, telling us we should all learn about algorithmic probability, wrote a very famous book in 1969 that showed that these particular learning machines that they thought would walk talk were actually quite limited in what they could do. And therefore that kind of killed the field for 10 years. Nobody could get any funding. Then it went back up again when expert systems came in. Lisp, some people may still remember that. It's going to change how we do everything. Then it all died. And then everything has changed around, say, 2012, which perhaps is one of the dates that people will count, because that's when Jeff Hinton, a very famous British-Canadian machine learning expert, and his students won a competition for looking at images and recognizing what they are. So I give you numbers 0, 1, 2, 3, but you can think about images of cats, dogs, horses, and a very famous one called ImageNet. And they didn't just do better than everybody else, they did much, much better than everybody else by huge amounts. Immediately, all the big tech companies started pouring money into this. So here's Sundar Pichai from Alphabet, Google, basically, who said AI is one of the most profound things we're working on as humanity. It's more profound than fire or electricity. They now want to call themselves AI companies as opposed to tech companies. And the claims are wild and crazy. And it's also true that these new techniques, deep learning techniques, have had an enormous impact. So very famously in London, DeepMind, now Google DeepMind, they won Go against the world's greatest Go player, Lee Sedol. That was thought to be an impossible task. They solved it. Very recently, they've used these to solve the protein folding problem. So how do you go from a sequence to fold the protein? It's an incredible, huge advance. There's no question that this is making a huge advance. Of course, these algorithms are affecting our lives in all kinds of ways. When you go on YouTube, these algorithms are showing you what comes up next, and so having a dramatic impact on our lives. So how do these work? So for those of you, I'm going to briefly talk about this for those of you who haven't seen this before. The basic idea is actually extremely simple. You have some inputs that you take in. So in the case of those images of zeros and ones, those would be the pixels. In fact, those are 28 by 28 pixels of 255 values of each pixel. So the 784 length vector. You look at each of those numbers, and then you multiply each of those numbers by a weight. Okay, it's very simple. You multiply something by another number, and then you might take another layer of nodes that you basically add up a whole bunch of weights of all the numbers, and you add them all up in the end. I guess you sum them all. And then if that sum is larger than a certain threshold, then you'll say that new weight is then up as a value of 1 or 0. If it's lower than a threshold, you can give it a value of 0, for example. And so it's an extremely simple method. It's very loosely inspired by the brain. And you can do this for a number of layers, and actually you can just iterate that a number of times. And at the end, everything can go to a final layer, for example, which will tell you if you have say, for example, you're only interested in zeros and ones, for example, it'll tell you it's 0 or it's 1, depending on its value. What you then do is you feed your system a whole bunch of images, and you adjust these weights, right? So I give you like a picture of a 0, a picture of a 1. I adjust the weight so that it gives me the right label. I do that with a whole bunch of images. Those are my training images. And once I've done that, that gives me the weights. And then if I give you a new image, it should, by multiplying by all those weights, give me the right label. Does that make sense? So it's a super interesting and simple idea. Now there's a problem here. So I just told you that statistical learning theory tells you that you need to limit the number of hypotheses that you include in your theories. And here comes a problem. The problem is that these systems are really highly expressive. That means, in fact, you can prove that for a network with a certain number of layers, you can reproduce any function that you could write down, including very complicated ones that you may be able to imagine. So they're extremely highly expressive. Another way of looking at saying this would be from this very famous paper, where they looked at a whole bunch of images. So these are images of boats and cars and animals, And then what they did is they shuffled the labels. So they just randomized the labels. So cats were called goats and etc. And they showed that you could actually train this thing to 0 error. So that this machine would give you exactly the labels that you told it to give, even though they have nothing to do with the real images. Of course, if you give it new images, I have no idea what they were, right? But it points that these neural networks are very heavily over parameterized. They can basically make any kind of mapping from images to outputs. And so here's another example of that, which is much simpler. So here I've got some data points, 10 data points. I can, if I fit a fifth order polynomial to it, you see I can fit it, but not quite get everything right. I have some bias problems, right? If I fit a 20 order polynomial to it, I can get 0 error. So I can exactly reproduce the data, but I get huge problems in data that I haven't introduced to it. That's a variance problem. But here, this green line is a bunch of different neural networks that I fitted with 1, 2, and 5 hidden layers with many thousands of parameters. And it gives you all this very smooth curve. It doesn't give you these kind of wild oscillating curves. And the question is, why does it do that? So do these neural networks break Occam's razor, right? So they are incredibly complex objects. So ontologically, they've got very large numbers of parameters. In fact, the current biggest ones have billions of parameters. They cost millions of dollars to train. And they're absolutely, so they are breaking Occam's razor as far as we can tell. Certainly the way statistical learning theory has thought to have captured the simplicity of the hypothesis cluster that you could use. And actually it's not a new problem, it's an old problem. It's a very famous statistician, Leo Breiman from Berkeley, who wrote this in 1995. He said, those are his reflections on 25 years of refereeing for a very famous conference. And he said he had a bunch of questions. And the first question he had was, why don't have an over-parameterized neural networks overfitted data? Overfitted data is basically what you expect to happen if you use too complex of a hypothesis. So what's happening is, I just showed you this bias variance trade-off before. As I make my model more and more complicated, what's happening is initially I'll see the bias variance trade-off, but once I get in the over-parameterized regime where I've got more more parameters and data points, I start seeing my errors going down. And that's the opposite of what you expect from a kind of simple Occam's razor type argument. So that got me very interested. So we've been working on that problem ever since. And so I'm going to give you a very simple example problem of how you might think about this and what you might, so that I think you can understand what these networks are actually doing. So this is a truth table for, let's say for you're a doctor, you have to do triage in the middle of the pandemic. People are coming to you and saying, should you send them to hospital or not? So, well, if you are, so I'll ask you 7 questions. You know, are you have a fever? Do you have a cough? Have you lost your sense of smell? Are you over 50? Do you have a heart problem? You're obese? You have diabetes, various kinds of comorbidities. And if you have all of those, I might send you to the hospital. If all of those, but you're young, I might still send you to the hospital if you've got comorbidities. If you are, you're not no comorbidities and you're young, I might say just stick it out in the hospital. Stick it out at home, sorry. I might not want to put pressure on your NHS, etc. Right? So how many of these questions are there? Well, there's 7 questions. So there's 2 to the 728 different sets of answers. And to each of those 120 answers, I can either send you to the hospital or not. So there's 2 to the 128 different Boolean functions that I can make with these truth tables. So the question would be, if I give you a bunch of answers, the doctor, can I then train a neural network to give the correct answers on the yet unseen questions? It's a very simple question. And by the way, how many functions are there? 2 to the 128? How many functions are there? So just remember, 2 to the 10 is 1024. Right? So 2 to the 128 is 1,000, basically 1,000 to the power 12.8, which is 10 to the 30, say 38, roughly 39, 38, which is roughly how many functions there are. So very large number. Right? So you might say, given that there's so many functions, I'll need basically, how can I ever predict anything about the future? In fact, even worse, there is a theorem, a set of theorems actually called no free lunch theorems by Wolpert and McCready that basically prove that if I give you, for this particular problem, it comes to the following. So if this is a Boolean function, so that what I'm trying to learn is what these outputs are given the inputs, right? And what it basically tells you is that, so if I don't know anything about the outputs, I just predict with probability 50% 0, 1, I'll have an average error of 50% or 0.5, right? I'll get half of them right, or half of them wrong. And that basically there's a proof, a very nice proof, that any learning agent, no matter how brilliant it is, when averaged over all target functions, all possible answers that the doctor could give, will on average work no better than a random learner. This is a kind of some kind of version of Hume's problem of induction. Don't complicate that. That's what it is. So a priori, you can prove that I can't learn this and do any better than a random agent. Yet obviously machine learning works. Billions are being pumped into it. We're told this is more important than fire. I don't believe that. But so the question then is, how can we think about that? So I had a very brilliant student who said the following: why don't we just try the following problem? We'll take this neural network and we'll just randomly pick parameters. So we'll do that in that problem I just had you. We're going to give it those 128 inputs and give it, say, half the output. So we'll give this first 64 outputs, and we'll train it that way. But before we do that, let's just ask ourselves, what was this thing going to do if I just randomly pick weights? So there's all these weights in here that I can have to calculate. And what he showed, which was quite surprising at first, but maybe not, if you think about the AIT theorem, is that functions that were simple were exponentially more likely to appear than functions that were complex. So a simple function would be a function that, for example, is all zeros or all ones. And these actually appear about 10% of the time. So if you randomly pick parameters in this thing, with a 10% chance, it picks functions that are all zeros or all ones, which are the simplest functions. I can describe that function with a very short description. And I can make other functions like 0, 1, 0, 1, 0, 1, 0, 1, or other simple pattern, repeating patterns. And I can make all those functions rather easily. And so this what we then found is basically there's a bias towards simplicity in these neural networks. It's exactly the bias that our coding theorem predicts. It's 2 to the minus the complexity of those outputs. You could do a lot more proving on that. It's not maybe not so interesting. And what you can then do is do a kind of Bayesian analysis of this. So I can define functions. So just to make sure I get this clear what functions are, have these images 50419, for example, then a function would be what the neural network outputs when it's given these images. So one function gives the right labels 50419. That's a function, right, from the images to the labels. Another one that gets one of these non-names right, one error right, and all possible combinations. Those are all different functions this can generate. So then I can write just a Bayes rule. So the probability of getting a certain function conditioned on my training sets is my likelihood times my prior divided by marginal likelihood. And the real interesting thing here is then what is the prior over functions? Well, we just showed you that prior function is highly biased for simple functions. What's nice about this kind of problems are that the likelihoods are often hard to calculate, or very easy to calculate here. Basically, the likelihood is the likelihood of data given the function. Well, it's either the function correctly describes data or it doesn't. So the likelihood is a 0-1 function. And therefore, the posterior is equal to so the posterior therefore is equal to the prior when the function describes the data. And you can also do this marginal likelihood, which normally Bayes don't care that much about, but in this case it's quite interesting because it's actually the sum over all functions that generate 0 error on the training set. And it basically is the equivalent to the likelihood that your learner will generate that particular mapping from inputs to outputs on random sampling of the parameters. And so that's what these neural networks are doing. They got this bias towards simplicity. And the question is, can we break this simplicity bias? Well, it turns out you can. I won't tell you about some more detail. You can play with some little tricks with them. And then what you can do is you can go from the system that I showed you at the beginning, which is highly biased towards simplicity. If you change the depth, so the number of layers, you change the width of the initialization parameters for these special neural networks, you can get rid of the bias towards simplicity. So it's like the Occam's razor you had that these things naturally seem to generate. This coding theorem, Occam's razor, starts to disappear. And so what you can then do in this, I'll show you what this does for performance. So here are, just look at this graph maybe for now, probability of getting a certain function versus the complexity of the function. This blue one is the standard neural network, and this yellow and this reddish one are ones that have been tricked. So they don't quite follow that that coding theory laws. They start going away from the bias towards simplicity. And what you see in this plot is the error you have on unseen data, given that you train, in this case, you train on 64 images and you also 64 inputs, sorry, and you also how likely you are to get error on the outputs. And you pick those outputs by some kind of target. So that tells you what the doctor answers. So the simplest target is just all zeros or all ones. This neural network that will predict really well. And as you get more complicated data, it has a harder and harder time. But this blue line is this normal neural network. This red one is a slightly different neural network, which is the one that's less biased to simplicity. And immediately it starts working much, much worse. And so why does it work much, much worse? I'll show you in the next plot. I'm going to give some intuition about, which is really important in AIT. So on the left, I'm going to show you the following. What's the probability that you get strings of complexity k, okay, of strings of 128? Well, it turns out you can do a counting argument that works like this. Actually, I'll just count with tens. It's easy. If I have strings of length 10, binary strings of length 10, there's 1,024 strings of length 10. There are 512 of length 9, 256 of length 8, and 208 of length 7. If you add all the strings that are shorter than length 10 up, they sum to 1,022. So there's not enough short strings to describe all long strings. So there's definitely two strings that can't be compressed at all, because to compress them, I need to use a shorter description. Half the strings of the strings that are shorter are taken up by strings that can only be compressed by 1 bit. Another quarter are 2 bits, etc. So most strings cannot be compressed. That's what you're seeing here. The probability that I get a certain complexity actually grows exponentially with the complexity. And most strings are complex, and very few strings are simple. That's the basic argument. Does that make sense? And so what's interesting is that grows as 2 to the power plus k. If you have a simplicity bias of 2 to the minus k, it exactly cancels that. And you get a more or less flat probability of getting any complexity of probability k. But if you're slightly below that 2 to the minus k, and because you're multiplying by probability to the plus k, which goes very quickly, you're going to be hugely biased towards complex solutions. And what this is basically telling you is the vast majority of functions that you can hypothesize are complicated. And if you've got a system that can in fact learn all those functions, unless you've got some very strong inductive bias in advance that tries to squash away those simple functions, you're not going to be able to learn. You're going to not learn well. And in this case, you can quantify these intuitions, and it suggests that this 2 to the minus k thing that comes out by itself is all that you really need. Good. Any questions at this point? I think I should get to the end pretty soon. Yeah. Yes, I'm going to jump. Because there's much more on this, but this is the main intuition. So it turns out that neural networks work really well. Okay, if the data is simple, right? So just to show you here, you see this in this very simple example. This is the normal neural network for simple functions, so simple truth tables. I can learn them really well. For complicated truth tables, I can't. The reason I can learn them very well is because there are actually not that many functions that fit simple truth tables. And so if I have some kind of learning agent that's biased towards simple functions, I'm going to, with high likelihood, find the function that's pretty good. If on the other hand, I've got a complicated function, then the new Fernandez theorem bites me. And actually it turns out I very quickly get into the regime where I'm basically like a random learner. Of course, the bias towards simple functions tells me that I'm biased against complex functions. So if I average over all functions, my simple learner will still give me, on average, no learning at all. But because I've looked at simple function, it's going to work well. And then why is that interesting? What does that tell me then? Well, it turns out that if you look at any kind of data that people have used in machine learning and deep neural networks, the data is all simple. So these are this one example I gave you from these handwritten digits to the labels. They're embedded in the 784 dimensional space. But if you do, you can work out what the effective dimension is of these systems. and they're typically on the order of dimensions of 10 or 11. So they're very low dimensional objects embedded in a very high dimensional space. So they're effectively simple in the Kolmogorov kind of sense. And so these neural networks, we're arguing, work really well because they're biased towards simplicity. And so what's happening here is a kind of interesting Occam's razor-like argument. So these overparameterized neural networks, which seem to break Occam's razor in first instance, because ontologically, they, in terms of the number of units that I postulate, there could be millions or billions or a very large number of parameters that I can fit. The number of functions that I could fit is extremely large. So the number of functions that my theory allows is extremely large. So that would seem to say that that's breaking a kind of parsimony argument. But because these things are implicitly biased towards simple outputs, they are they're exponentially biased towards simple outputs. They therefore are exponentially more likely to pick the simple function of the complex functions. And if your things you're trying to learn are actually simple, that's a good bias, and that means you can actually learn something. And we argue that so Occam's razor is, as it were, saved in this very specific kind of case. And you can understand Occam's razor a little bit in the sense that you can only really learn simple things, because simple things are the only ones where if you don't know anything more about the system than the data that you're given, they're constrained enough that you can pick functions that are going to do well on the things that you don't know. So this is a nice, I think, example of kind of how Occam's razor works in the topic of machine learning. I think there's lots of interesting kind of subsidiary questions that you can ask yourself about how that goes. Now, I'm going to give about 5 minutes. I'm going to talk about one more example, and then I'll come to a very kind of wild conclusion. So I'm going to jump from this topic of machine learning to a different kind of topic, which is Darwinian evolution. So Darwin's great idea was that there are 2 steps to evolution. First is variation. That is to say, your offspring are different from you. And there's natural selection, which basically says if that variation gives some kind of advantage, then that will dominate the population. It's actually quite simple. So if, for example, my genes mean that my offspring will have, on average, I'll have on average 2 children, which each have 2 children over many generations, and Simon's has 4, and each of them have 4. And after a few generations, Saunders' genes will dominate our population. That's what natural selection is basically telling you. And what's kind of interesting about this is to ask yourself, how big are these spaces of possibilities in biological systems? So here are 2 very important biomolecules. One are proteins and one is RNA. So proteins are made of 20 different amino acids that are in a linear chain. So how many proteins can you make? Well, if I make every length 37 protein, that's 20 to the power 37 different ones. That would already weigh more than the Earth. That's actually an extremely short one. But every length 58 would weigh more than the observable universe. And every length 476, which is the mean length of protein in your body, weigh 10 to the 500 times the weight of the mass of the visible universe. And if you like numerology, 10 to the 500 is the number of possible multiverses you get from Calabi-Yau manifolds. So there's clearly some kind of connection there. And RNA has the same thing. So RNA is 4 different letters, and so it's 4 to the power length, and there's like 126. Make sure if you made every single possible one, it'd be more than the weight of the Earth. And the reason I want to talk about this is I think that this is talking about something. There's a kind of possibility space here. It's extremely large, unimaginably large possibility space, hyper astronomical, because it's larger than any kind of universe. And the question is, can this coding theorem tell us something about looking in these kinds of spaces? So I'm going to jump to an analogy. This is a very famous book by the Argentine writer Borges, where he has a library of Babel. And this library is every book. They got exactly 47 pages with 40 lines each, 80 characters, 22 letters of the alphabet. And so in the story, people go into this library and looking for their vindication, which is a book about their lives. And there is in that library a book that describes every aspect of my life, including at this moment, as I'm speaking to you, a meteorite hits and blows it all up, and every possible variation thereof. And so, Borges points out that they may find many books that seem to describe their lives, may be deceptive in some way or the other. So every book is equally likely, but every story may not be equally likely. Some stories are very complicated, would take all 410 pages to write. Some stories may be rather simple. It can be written in many different ways in the same book. So I might expect that if I start thinking about stories, like I extract in some way the concept of the story, and look in there, I find certain stories with much higher frequency than others. And so the only bit of this I want to tell you about is it turns out that if you look at, I'll tell you once, this is the last story I'll tell you, you can think about this in evolutionary terms. And so I got interested in this is how I got interested in this whole question of the coding theorem. Came from this experiment by Jack Shostak, the Nobel Prize winner, another great genius and creative mind in this area, who did in vitro evolution experiments. So what you do in vitro evolution is you do it in your lab. And RNAs are really interesting because they can transfer information like you learned in school. They can also be catalytic like proteins, and they can do particular kinds of tasks. And so he said, I'm going to just take these RNAs and I'm going to randomly mutate them, and I'm going to select them such that they will have some kind of enzymatic activity called self-cleaving enzymatic activity. That's it, very simple. He ran that experiment and was able to do so in the lab. That's very exciting because you can use this to design new catalysts. But the fascinating thing is every time he did it, he found exactly the same structure. So I thought to myself, well, how long are these RNAs? They're about length 55. How much does every strand of length 55 weigh? It's about 10 to the 10 kilos. He only used about 1/100 of a gram of material, so about 1 in 10 to the 15th of this space of possibilities he used. And every time he did it, he found the same structure. That's very surprising. It's a bit like putting your hand into a haystack and always finding a pin. Right? And it's exactly the same pin each time. Right? So how does that work? And so it turns out you can solve this problem of folding numerically. So this is a sequence that folds this kind of structure. I can abstract that structure out to a simpler version of who binds to whom. And then what you can do, which I think is quite interesting, is you can basically count how many different sequences map to a particular structure, like this structure. So how many sequences will fold with this as the ground state for energy. And when we did that, what we found, this is for length 55 ones, that we think there's about 10 to 13 structures. We worked out a way of calculating this. We then looked at here on the y-axis is the number of sequences that map to a particular structure. This is just ranking them from 1 to a very large number. And what we found is that the 500 found in nature are all these ones that have many different ways of mapping to them. So these are the simple stories. There's many ways of telling the story. Okay? There's many ways of folding this RNA, a very, very large number of them. There's 10 to the 20 ways of the sequence that will fold into those RNAs. And those are the ones found in nature, including this particular structure that he found in his experiments were there. Does that make sense? What's even more surprising is we did a few little tricks. I'll bore you with what we did, but we made a slightly simpler version of the structures, and we simply calculated randomly sampled sequences. Okay, that's like randomly typing on the inputs, and we fold them. That's like the little computer that folds them, and then we look at the structure that comes out. We did this many, many, many times, and we then rank them from the most likely to the least likely. So this one's a very likely structure for 55. It's for length 126, which, by the way, remember, was the length that I made every single one, way more than the mass observable universe. And we rank them. And then the yellow ones are the ones that are found in nature. Okay. So for example, for RNA, we think that there are about 1 trillion possible structures. There are only 63 that are found in nature out of 1 trillion. And those are all the ones that are most likely to appear upon random sampling. Here, and for length 55, a slightly different way of looking at the structures, there's slightly more of them come out. It's basically the same story. This is very surprising because what this is telling me is that the RNA structures that are used in nature, in life, are an extremely small subset from all possible ones. And they're the ones that are most likely to appear. And in fact, as you might not be surprised to know, they're also the simplest ones. So if I look at all possible RNA structures, or normal, what this detail means is how likely something to appear versus complexity, and you'll see that the complexity of a structure, so how much information I need to describe it. So I can take the structure. In this case, what we did is you can write these structures out as binary strings that will describe them in a unique way. Then I literally put that into a compressor, which is very similar to the kind of compressors you have on your computer. And then that will tell me how likely they are. So here, for example, I say how long the sequence is when I compress it from 7 down to 95. This is how likely it is to appear, which is 10 to the minus 1, 10 to the minus 8 probability. And so the natural ones are all in this area up here, the ones that are most likely to appear. And so the story there, basically, and that's the kind of the final story, is that these RNAs that you see in nature, and actually we've written a paper recently, we showed this holds true for a wide range of other biological systems. The ones that you find in nature are the ones that are simplest. So evolution turns out to have a kind of inbuilt Occam's razor. Random mutations, or like randomly typing on the inputs, the outputs that it generates, in these cases of structure, are exponentially more likely to be simple ones that have short algorithmic descriptions. And therefore, those are the ones that nature turns out to use. It was quite surprising. This was quite surprising to me that this worked so well, because it tells me that actually, for example, for the RNAs, we think that's a very popular hypothesis that early life was RNA based. And so the argument has always been, how could you, from a space that's hyper-epsilonically large, find anything that would make something that's alive? And the argument here is, well, that's because these things are exponentially more likely. The ones that apparently these ones that are exponentially more likely to appear have everything you need for life. So although the space of possibility is extremely large, the number of possible stories is extraordinarily large. There's a subset of very simple stories that are all that nature has needed to make life in all this complexity appear. So I gave you a brief overview of simplicity, tried to argue that it's more complicated than you might think. I then use AIT to give this coding theorem that in certain instances shows you a kind of intrinsic bias towards simplicity. I showed that coding theorem helps resolve a famous conundrum in deep neural networks, which is why do they work so well, given that they're over-parameterized, given that they seem to break Occam's razor. It's actually Occam's razor comes back to save Occam's razor, as it were. And then in evolution, I show that you get this intrinsic bias towards simplicity, which apparently is what nature tends to use. And this comes to my crazy idea, which I have down here, which is maybe there are other scientific fields when we try to look at something, somehow something like this coding theorem is working and is therefore generating simple theories. Maybe there's a kind of universe generating process that was biased exponentially towards simple universes, which is why we have relatively simple laws. And of course, if you have relatively simple laws, then something like Occam's razor is going to work well. That's a sufficiently crazy idea that I should leave it in the category of crazy ideas. But I wanted to end there with the idea that if it's true that we have a rule that's generated by lots of algorithmic processes, and these processes will probably be biased towards simplicity, and if that's true, then trying to back out what is happening will benefit from something like Occam's razor. And I wanted to end with that. So thank you for your attention. Apologies for running over by so much.